Hey everyone, welcome to another session of Ceerazzledazzle Physics. In this video guys, I'm going to be doing a full GCSE physics revision video on the topic of radioactivity. If you're still struggling with any of the content after watching this video, please check out my YouTube channel, which I've got all the bite-sized versions of every single topic to help you with your studies, going through it at a slower pace. Alright, let's get straight into it. 3, 2, 1. Right, atomic structure. So over here we have an atom. We can see we've got protons and neutrons inside the nucleus over here. Electrons are orbiting over here. Here are my symbols. So proton, there we go, is a charge of +1. Think of P for proton, meaning positive, the relative mass of 1 as well. Neutron has a charge of 0, it's neutrally charged. Think of neutral over here. Relative mass of 1. The electron over here, it's orbiting the nucleus and it has a charge of -1 over here. Its relative mass compared to the other ones is going to be 1 over 2000 for this one over here. Right, now nuclear notation. So sometimes you'll see chemical elements over here and they're represented in this fashion over here. There's a number at the top, a number at the bottom. The top number corresponds to the number of protons and neutrons. The bottom number corresponds to the number of protons. Yes, this was going to be the atomic number at the bottom and the mass number at the top. And the chemical symbol goes over here where the X is. So look, this is helium 4, 2He. The reason why it's 4 is because there's 2 protons and 2 neutrons. In total, there's 4. But there are 2 protons. That's the reason why the bottom number is 2 over there. And yes, the proton number is usually the number of electrons as well. So there we go. So 2 protons and therefore there are 2 electrons as well. The radius of an atom is going to be 1 times by 10 to the minus 10. And the radius of a nucleus is roughly 1 over 10,000th of the radius of this atom over here. So just make sure you recognize that the nucleus is tiny compared to the actual radius of the entire atom itself. Isotopes. Isotopes are atoms with the same number of protons but a different number of neutrons. So over here we've got 1, 2, 3 different isotopes of helium. This one is helium 4-2, this one is 5-2, this one is 6-2. As you can see that they have the same number of protons. Red is protons, yes, so 2 protons, 2 protons, 2 protons, but the number of neutrons are changing. Hence why it's going to go from 4 to 5 to 6, because this one, there are 2 neutrons here, so therefore there's 4 nucleons in total. This one is 5 in total in the nucleus. This one is 6 in nucleus, hence why it's over here. So isotopes have the same number of protons but a different number of neutrons. History of the atom. You've got to be aware of how the model of the atom has changed as time has gone on and how we've discovered new things about the atom. So first of all, there was a model that basically atoms were tiny, spherical, indivisible, over here, and then we moved on to the plum pudding model. It was just going to be a giant positive charge, a solid block, and negatively charged electrons embedded around it. Very similar to a pudding. Yes, that's the whole point. It's a plum pudding model. Some kids don't like that. You can think about it as a chocolate chip cookie, and the electrons are like the chips which are embedded within the cookie. It's the same idea, but it's a giant positive charge and there are negatively charged electrons embedded. There is no free space in this and the electrons are not free to move. And then from here we move on to the Rutherford's model over here, which is the nuclear model. He found out that in the center there's a positive charge over here in the nucleus. This is called the nucleus and it's positively charged, and electrons are orbiting it over here. Electrons are orbiting it over here. Make sure you can identify that there are no neutrons right now. The reason why, they haven't been discovered yet. But there's a big flaw in this. So obviously if this is positive, this is negative. Hopefully that you can see that they would collapse because they would be attracted towards each other. So that led us to the Bohr's model of the atom, in which he stated that there were protons and neutrons inside the nucleus. The neutrons were discovered by James Chadwick, and the electrons are orbiting in fixed shells. So now they are electrons in fixed shells, not just whizzing around it in an orbit over here. And the electrons, because they are in fixed shells, they cannot drop down. Right, how on earth did we get to Rutherford's model? It's going to be via the Rutherford alpha scattering experiment. So what he did was this. He took a radioactive source which was going to emit alpha particles. For now, just accept that these are some radioactive particles which are positively charged. So positively charged particles are coming out of this source over here. There's a lead-lined container around it to just block off any alpha particles which might go back. And then the alpha particles are going to travel across. He fired them at a thin layer of gold foil over here, and he put a Geiger counter on the opposite side over here. The Geiger counter detects the alpha particles. Every click the Geiger counter receives tells you that an alpha particle has been detected. And look, I've got a counter over there. So obviously if loads of them can pass through, this number goes up. Here are his results, guys. So look, you can see that most of the alpha particles pass straight through. Some of them were deflected, okay, and then very few of them were deflected at extreme angles. Very, very few of them are deflected at extreme angles. What did that mean? Right, so look, this diagram is what I usually use to explain it. So look, I've got the alpha particles going over here, and look, they're all going across. And this is the atom, the atom that obviously he was proposing. This kind of makes sense now because you know that most of the atom is empty space, hence why most of the alpha particles can pass straight through. So look, this one passes through, this one passes through, this one passes through, and these ones at the bottom over here. Then, as some of the alpha particles get closer to the nucleus, hopefully you recognize that the alpha particle is positively charged, the nucleus must be positively charged because it's going to deflect them away because like charges repel. And that's the reason why it deflected away over here. And then some of them were deflected by extreme angles over here. So what does that mean? That means that the nucleus is a tiny concentrated mass within the atom itself. That's why it's very hard to fire at it directly and hit it head on. So look over here, we've got the following observations. Most of the alpha particle passes straight through because most of the atom is empty space. Some of the positively charged alpha particles were deflected. The reason why is because they are repelled away from the positively charged nucleus. And last of all, very few alpha particles were deflected by extreme angles, almost 180 degrees. The reason why is because the positively charged nucleus is a concentrated mass over here. Make sure you know the difference between these two, the last two. As most kids get them confused, make sure you know the difference. Electron transitions and radiation. So let's say we have the atom over here. First of all, an electron can move to a higher energy level. So it can go from this one over here to upwards over there if it absorbs an electromagnetic wave. So look, I've drawn it over here. So look, we have this one over here. We have this electron over here. So look, an electromagnetic wave can come in. This electron can absorb this energy of this electromagnetic wave and move upwards to a higher energy level. So there we go, the electron is promoted to a higher energy level. And by reverse, let's say you had an electron at the top right now, but it wants to go back down. Obviously, it drops back down to this lower energy level, releasing a corresponding electromagnetic wave. Radioactivity, right, so first of all, let's say we have a nucleus of an atom over here. First of all, the nucleus is stable, nothing will happen. Yeah, nothing will happen here, it's just stable. Yes, like most of the stuff around us. But if the nucleus becomes unstable, usually when it's too heavy, what happens, it will break down. Yes, and this is known as radioactive decay. So when the nucleus breaks down, this is known as radioactive decay. In a decay process, what can happen is the large unstable nucleus can break down and it can become into two smaller pieces, and sometimes you might get alpha radiation coming out, beta radiation coming out, gamma radiation coming out, or neutrons. Sometimes only one of them, but I've drawn all of them over here. And energy is released in this whole process. So when a decay process happens, we get all of these things possibly coming out. Right, so how would you detect alpha, beta, and gamma? So let's say obviously the decay process occurred. How would you detect alpha, beta, and gamma? First of all, you can use the Geiger counter. So look, you can put your radioactive source over here in a lead-lined container. Yes, the reason why we'll come across that in a minute. And what happens is the alpha particles travel outwards and the Geiger counter will click every time an alpha source is detected. Yes, or beta source or gamma source over here. The activity is basically the amount of radioactive particles detected per second. There we go, the amount of ionizing radiation detected per second. The units of activity are called the becquerel, capital B, lowercase q, the becquerel over there, or counts per second or counts per minute. Right, background radiation. Background radiation is the radiation that naturally surrounds us from our environment. It is dependent upon many factors including jobs and location. These are the naturally sourced ones over here. Radon gas from rocks and buildings, cosmic rays from space, radioactive material in food and drink. Man-made ones, so obviously if you do these jobs or you're around these areas, you will get exposed to more radiation. X-ray equipment, imaging, nuclear fallout from nuclear weapons, so if there's a nuclear disaster in the area, nuclear accidents such as Chernobyl or Fukushima. Obviously if you live near a nuclear power plant which obviously collapsed, you'd have more radiation. The radiation dose is measured in sieverts, capital S, lowercase v. Investigating radioactive sources. So let's say you were asked to actually measure the radioactivity of a source. First of all, you should measure the background radiation in the room. So you have the Geiger counter, you measure the background radiation in the room, which is going to be my green arrow. Okay, so let's say right now I measured it for 1 minute, I've got 10. Yes, 10 clicks in 1 minute. Then if I was to put a source in front of me, I would measure the count rate again. So let's say it's 180 over there. So obviously, the reason why it's higher is because now you have the source plus the background radiation. Therefore, to work out the activity of the source itself, you simply take this value and subtract the initial value over here. So the count rate of the source is equal to the count rate of the source plus the background radiation, which is this one, subtracting the count rate of the background radiation over here, subtracting this one over here. So it's going to be 170 is actually coming from the source. because you've excluded the radiation from the background radiation. Properties of alpha, beta and gamma. So this table you should hopefully memorize that we've got alpha, beta and gamma over here, and I've got the symbols of them. Alpha 4,2, description of alpha particles, 2 protons and 2 neutrons, like a helium nucleus. The charge is +2, why? It has 2 protons. Relative mass is 4 because there are 2 protons and 2 neutrons. Each one of them is worth 1. It is stopped by 10 centimeters of air, okay? And it's the least penetrative, but it is the most ionizing. I'm going to come across these 2 bits later on, so don't worry. Beta, symbol of 0, -1, beta over here. It's a fast moving single electron, the charge is -1. The relative mass is 1 over 2000 because it's just an electron over here. It is stopped by thin metal sheets. Yes, it can pass through paper, but it is stopped by thin metal sheets. The penetrative ability is moderate, ionization ability is moderate as well. Then gamma over here, 0, 0, yes, because it's a wave. It's an electromagnetic wave, there we go. The charge is 0, the mass 0 as it's a wave, stopped by thick lead or concrete. Penetrative ability is the most, it can pass through the most. Ionization ability, it is the least. And here's a nice visualization of the penetrative ability. So look, alpha, stopped by paper, beta, pass through the paper, stopped by thin metal sheets. Gamma, pass through the paper, pass through the thin metal sheets, but stopped by the thick lead or concrete. So as you go down the group, the penetrative ability is increasing. Nuclear decay equations, right, so when a nucleus undergoes a decay, alpha, beta or gamma, the nucleus will change itself. So we can look at how the atomic mass and the atomic number changes. So over here, look, we've got 235, uranium 92. So first of all, if it undergoes alpha decay, the alpha decay leaves, taking a 4,2 away with it. What happens to the nucleus that's left over? Obviously, I must subtract 4 from the top number and 2 from the bottom one. But look, they balance out. 235 uranium goes to make 231 thorium, plus the 4 over here. So these 2 numbers add together to make this number over here. 92, obviously, it becomes 90 because the 2 is taken over there. For beta minus decay, look carefully, the beta is 0 minus 1. So look, the mass number remains the same. 235 goes to 235 because 0 is over here. These 2 add up to 235. But careful with this one, we notice that it is 93 because it must be 93 minus the 1 makes me 92 over here. So in beta decay, one of the neutrons inside the nucleus is converted into a proton, hence why the proton number goes up over here and the beta particle is emitted. There we go. Right, now gamma decay. As you can see, gamma 0, 0, therefore the mass number remains the same and the atomic number remains the same as well because it makes no change over there. So 235 goes to 235 plus 0, 92 goes to make 92 plus the 0 over here. This bit's a bit extra, but beta positive decay. So yes, beta particles can be a positive version of it. As you can see, in beta positive decay, 1 proton in the nucleus is converted into a neutron. So we're going from 1 proton in the nucleus is being lost and being converted into a neutron. That's why, look, 92 goes to 91 because we've lost a proton, but the mass number remains the same. And the beta positive particle takes away with it the 0 and 1 over here. Ionization ability, right, so I usually use this to explain ionization ability. We can see that we've got alpha, beta and gamma, and let's say we fire them through a group of atoms over here. First of all, to ionize something is to rip off an electron from an atom. So we can see that as the alpha particle moves through it, because it has a charge of +2, it can knock out the most electrons. So that's why it's highly ionizing, but it travels the least distance. Beta particle, it's only a charge of -1, so it can knock out a bit more than the alpha. And gamma is the least ionizing, so therefore it interacts with the least amount of electrons over here. So we hopefully can identify that alpha, beta and gamma as you go up. So alpha is the most ionizing, beta is the moderate one, and gamma is the least ionizing. Half-life. The half-life of a radioactive sample is simply the time taken for the number of nuclei within a radioactive sample to decrease to half of its initial amount. Right, so let's say we gave you all these nuclei over here, red, they're undecayed, but as time goes on, they're going to decay. So look, they all turn blue over here. So obviously as time goes on, they all decay. If I was to plot the graph of number of undecayed nuclei, so look, we've got loads at the start, okay, and as time goes on, they will decay. So as you can see, guys, as time goes on, the number of nuclei decreases. Over here, it's an exponential curve downwards. Right, so now from here we can actually look at the half-life on this graph. So look, the half-life to work it out. So first of all, the initial amount is 1,000. You simply look at where 500 is and read off the graph over here. So the time taken for the nuclei to drop down to half of its initial amount is obviously from 1,000 to 500. It's only going to be 10 seconds for this radioactive sample over here. Make sure you draw that on the graph over there. Right, so now from here we're going to look at the uses of nuclear radiation. So over here, this is the physics behind a smoke alarm, and it actually uses nuclear radiation. So here we've got a cell, and we've got a terminal over here, and they place an alpha source on one side. Right, so the alpha source over here, what's going to happen is obviously it will emit alpha particles, they will travel across the gap over here. So now look, you've got a flow of charge because the alpha particles are charged, they can cross the gap, there will therefore be a current as it goes around the circuit. But then when there's a fire, what happens is obviously smoke particles enter the chamber, right? So now look, the alpha particles are blocked from going across, and therefore the circuit identifies that there's a drop in the current, and hence the alarm sounds. And this is the reason why we actually use alpha radiation inside a smoke alarm. Right, using beta decay to measure the thickness of foil. So how they actually keep the foil that's in your kitchen like that thin is going to be via this method. Right, so over here you've got some giant bit of metal coming in, all right, now so a sludge, and what happens is there's two rollers here. The rollers are designed to squash all that metal into a nice thin strip over here. So there we go, it enters on one side and it uses the rollers to squash them over here. So what they do is they put a beta source on one side of what's coming out. So this is the very thin strip coming out, and a Geiger counter underneath it on the opposite side over here. So the beta source is going to emit the radiation, it's going to travel down and through it, and we will get the Geiger counter getting a reading because some of it can pass through. Right, so simply by looking at the Geiger counter you can determine the thickness of the foil. So over here we can see that the thickness of the foil has gone up from 100 to 200 over here. So what does that tell you? So obviously that means that if there's loads more radiation being detected, that tells you that the foil is too thin, okay? And therefore you can separate the rollers to increase the thickness of the foil. And what about this one over here? Let's say that the count rate drops down too much. Obviously, if the count rate drops down too much, that means it must be too thick in the middle. That's why less beta particles can pass through. And therefore, if it's too thick, you can move the rollers closer together to squash it to make it thinner. Medical traces. So let's say, unfortunately, someone has a tumour over here in an unknown location within the body. So first of all, we can use a radioisotope medical tracer to pinpoint its location. So the person ingests a radioisotope, it goes inside the body. The radioisotope then is expelled, it's going to travel out of the body over here, there we go. But because you have a tumour, the tumour will absorb an excessive amount of the radiation. Okay, so the tumour absorbs a large amount. So let's say then after a period of time you were to come back to the patient and you look at the radiation that it's should be given off, you would find that most of the radiation would have disappeared, but because the person has a tumour which absorbed a large amount, it would still be given off the radiation. And hence that's how you can find out the location of a tumour using a medical tracer. Right, so now from here, when choosing a radioactive isotope tracer, you obviously must look at the dangers and the half-life of the sample. First of all, the reason why gamma is chosen because you know it can pass through the skin and it can pass outside of the body. Yes, it can pass outside of the body over there. It is also the least ionizing, so you don't want to put alpha inside the body. And then, first of all, the half-life. You do not want it to have a very long half-life because the person will be exposed to a large amount of radiation. Nor do you want the half-life to be too short that you can't actually carry out the experiment. You don't want it to put it in the body and therefore it quickly leaves it over here. So you don't want a too long half-life, not a too short half-life over here. So make sure you are aware of that when choosing the radioactive medical tracer. Next one, the gamma knife. So the gamma knife is this. Let's say you have a tumour, let's say in a location in your head. First of all, you just put radioactive cobalt sources at different angles over there around you, and obviously they fire out the radiation, and hopefully where all the beams cross over here, it targets the target area and destroys the cells over there. So yes, alpha, beta and gamma are all ionizing, and yes, they can lead to changes in your DNA and therefore mutations and lead to cancer, but it is, as you can see, it can be used to treat cancer as well. Right, so the half-life and half-life calculations. Right, so first of all, radioactive dating. So this is how we actually work out how long something has been dead for. It's via the process of radioactive dating. This is a person over here, and first of all, every single person alive is constantly taking in carbon-14 from the food that you eat. Carbon-14 is a radioactive isotope, and it decays as time goes on. It has a half-life of 5,700 years. Okay, so it has a half-life of 5,700 years. Okay, so right now let's start with the following. Let's say we have 1,000 grams of carbon-14 taken into the body right now. Okay, let's say this person over here has 1,000 grams. But let's say if the person dies, what will actually happen is obviously you're not taking in any more carbon-14, it will decay. So the amount of carbon-14 inside your body will decay as time goes on. So as you can see, the amount of carbon-14 has decreased over here. And that process to go from 1,000 to 500 is one half-life, because that is the definition of the half-life. So that would take me 5,700 years. So here's a good example of reactive dating. So look, a fit person should have 1,000 grams of carbon-14 inside them. A body is found with 125 grams of carbon-14. The half-life of carbon-14 is 5,700 years. For how long has the body been decomposing? The way you tackle this question is the following. So we've got 1,000 grams over here when you're alive, but the body that you found has only got 125. First of all, you know you should have 1,000, but you've got 125. Work out how many half-lives have passed. So look, it's going from first half-life, second half-life, third half-life over there. So 3 half-lives have passed to go from 1,000 to 125. And then from there, you know each half-life is worth 5,700 years. Therefore, it's just going to be 3 times that. There we go, so 17,100 years. If you're still struggling on this, I've got loads of videos on me going through difficult half-life questions in the description below. Right, now, nuclear fission. Nuclear fission is the process in which a large stable nucleus splits into small, lighter nuclei releasing energy. The energy comes from the mass difference between the initial nucleus and the products afterwards. So the mass of this nucleus is not equal to the mass of this one plus this one. Why? Some of the mass has been converted into energy. So induced nuclear fission. So this is what occurs inside a nuclear reactor. Basically, they have uranium, yes, which is stable, or yeah, over here. What they do is they fire a neutron into it, and then, look, you know the neutron goes in, it becomes unstable, and then it starts to split. There we go. It actually splits off into 2 daughter nuclei, because they come from the parent, that's why it's called daughter nuclei, and 3 neutrons are released, plus energy. Okay, and look, over here you can see that 1 neutron goes into uranium, it becomes uranium-236. Krypton barium are released and 3 neutrons plus energy is released in this process. Right, so there's something interesting that happens to these 3 neutrons which are released. Those 3 neutrons released from the initial fission reaction. Yes, this is called induced fission because you are triggering it with the neutron. That's why it's called induced fission. The neutrons released will then hit other uranium nuclei and they will then split themselves. So from one initial neutron we're getting this split, these splits and these splits occurring over here. And therefore, each time this occurs, energy is released in the whole process. Right, so now, how would you control this? This can actually spiral out of control with too much energy being released in a short amount of time. So the simplest way is to absorb the excess neutrons. So you can actually put like blocks inside, you know, these are called control rods, and they are placed inside to absorb the excess neutrons. They are made out of boron. So the excess neutrons are absorbed by the boron here. Now let's look at all of this within a nuclear reactor. So hopefully you remember that a nuclear reactor core is going to produce energy in the form of heat. It then heats up the water, which turns into steam. The steam then goes through the turbines turn, which connects to the generator, which creates electricity. So what does a nuclear reactor core look like? It looks like this. There are things which are called fuel rods, which are separated. Yes, they're not touching each other, they're separated. In between each of these fuel rods, there is a control rod. Okay, the fuel rods contain the uranium or whatever fuel that you're using, could be plutonium over here, and the control rods are over here. The control rods can be raised or lowered. The whole thing is has been encased in concrete. Yes, the reason why it stops all the excess radiation being emitted to the surroundings over here. Right, and look, all of it's in water. Yes, and there's a heat exchanger over here. So looking over here, we can see that when a neutron is fired in, what happens is, yes, the uranium splits, releasing neutrons, and they can then travel into the other fuel rods, causing multiple fission reactions to occur. But let's say the reaction is happening too fast, you simply can insert the control rods down, and obviously they block off the neutrons and obviously slow down the rate of the nuclear reaction. So that's the use of the control rods. And over here I've got a table just summarizing it. Fuel rods contain the nuclear fuel which will undergo the fission. Control rods are raised and lowered to absorb the excess neutrons. There's also a moderator which slows down the speed of the neutrons so that they can be easily absorbed by other uranium nuclei. So that means that if, imagine the neutrons are traveling too fast, a uranium nucleus can't absorb it. It's like someone throwing a ball at you really fast, you can't catch it. The heat exchanger is used to remove heat from the whole system, so therefore it doesn't overheat. And then shielding is the concrete shielding on top, just to prevent the radiation from escaping. Nuclear fusion. Nuclear fusion is the other process. So rather than having nucleus splitting and releasing energy, you can take 2 lighter nuclei, combine them into one which is heavier, and that will release energy. It's almost like the reverse. So nuclear fusion is the process of when 2 lighter nuclei combine together to form a larger, heavier nucleus, releasing energy in the process. Okay, the energy comes from the mass difference again. So the mass of these 2 will not be equal to the mass of that because some of the mass has been converted into energy, which is going to be released over here. The reason why this is difficult is because, don't forget, both the nucleus are positively charged. Yes, there's loads of protons there, loads of protons there. Therefore, they will be repelled from one another. So therefore, you need high temperatures and high pressure for this to occur, which are really difficult to achieve on Earth. Nuclear fusion, though, can be found naturally within all the stars. So all the stars are powered by nuclear fusion. They are fusing hydrogen into helium. So they get hydrogen, it's fused into helium, and that's what produces the energy which we have on Earth over here. The differences between nuclear fission and nuclear fusion. Nuclear fission, large nucleus splits into two, releasing energy in the process. The energy becomes from the mass difference. Nuclear fusion, smaller, lighter nuclei combine to make a larger nucleus, releasing energy in the process. Energy comes from the mass difference again. Nuclear fission, there's a finite amount of uranium and plutonium available. There's only a limited amount on Earth. But nuclear fusion, if we manage to solve this and actually get this working, there's an abundant fuel. Imagine if we can actually fuse water. Water could be theoretically used, could potentially solve the energy crisis. Per kilogram of fuel, fission releases less energy. Per kilogram of fuel, fusion releases more energy. Fusion reactors are easy to get started and the science behind them is well known. Fusion reactors are very difficult due to the high temperature and high pressure. And last of all, the difference between contamination and irradiation. Contamination is when a radioactive material actually physically gets transferred onto something. I always give the example of, imagine a fly, it touches something dirty and it lands on your food, it's contaminated it. It's actually transferred the physical matter onto something new. So if something radioactive has actually physically attached itself to you, you've been contaminated. Irradiation is different. It is simply being exposed to the radiation. So as you can see over here, the radioactive material hasn't touched the person, you're just being exposed to it. So there is a difference between contamination and irradiation. And that's it for another session of Ceerazzledazzle Physics. Make sure you hit the like and subscribe button to get my channel going, and good luck in your studies. Ciao, ciao, and goodbye.